Ladder problems is our subtopic and equilibrium of rigid bodies. So, I'm going to use something when we are going through these ones. So, the following, we are going to see the cases, most common cases in ladder problems. And we are going to start with case 1. Ladder resting on a smooth vertical wall and the other end on a rough surface. Now, this is the case we are having. Let me put it here. This is the case we are having. We are going to assume this is our ladder, and this is the vertical wall, and this is the surface. Now, whenever there is contact, we expect reaction. So that's why, even if this is a smooth wall, but there is contact, so we are going to expect reaction. That's why we have reaction, and this reaction is always perpendicular to that point of contact, as you can see there. So that is the case here. But now, we are also having a contact on our horizontal. So this is the case we have. We have a contact on our horizontal. We expect also the reaction, which is perpendicular to that surface where there is contact. That's why you see here, there is a contact. I mean, it is perpendicular to that surface. Now, because this surface here, this one is smooth, the wall is smooth, but the contact here, they are telling us that this is a rough surface. And if I will have surface, now when we put this roller like this, if it's to slide, it's going to slide going the other side. I think that's when I put it to slide, it's going to go the other side. So if it slides the other side, always the friction is opposite motion. So if it's sliding going the other side, friction is going to be opposite this side. That's why we have friction going the other side. So that's case 1. When it comes to case 2, rudder resting on a rough vertical wall and a rough horizontal surface. So both the wall and then the surface, all those two are rough. Whenever there is contact, reaction. That's the thing that should stick in your head. Any contact, there is reaction perpendicular to that surface. Even here, there is contact perpendicular to that surface. But because these two are rough, that's why when this ladder is trying to slide, going this side, you see when it goes this side, because when it slides, it's going to go down, and then this side is going this side. So when it's sliding, you see that it's going the motion, I mean it's going in this direction. So friction is going to be opposite. That's why you see our friction is there. When it's going this side, friction is going to oppose. That's why it's going this side, as you see there. Always we have weight of that ladder, and always weight is acting in the middle of that, as you can see there. Okay. Then let us come case 3. Ladder resting on a smooth vertical wall and a smooth horizontal surface with a string tied on the foot of the ladder. Foot means where you step, or where there is the last part of that is all resting on the floor or horizontal surface. So this is what we call a foot of this ladder here. So now they are tying the string. They are tying the string from here up to here. Because this is smooth and this is smooth, we expect that this thing is going to slide. Now, keep it in equilibrium. It means that we shall tie something so that this end cannot move to avoid that sliding. Now, this is something we are tying now. We are tying this string at the base of the wall, the vertical. Now, it means that this ladder is going to be trying to push it in that direction. So, meaning we are going to have some tension. So that's how our tension is going to be in that case. Now this one is a string, or staying as a string. This is a smooth surface, so don't expect anything like friction. So even this is smooth, but there is contact. That's why I have reaction, and also of course the weight. Case 4. Ladder hinged on a smooth horizontal surface while the upper end rests against an over horizontal bar. Now, in the last lesson, I told you I'm going to show you what we call a peg. A peg and a hinge, they almost go like this here. So when I rest something like this, this is the case I'm having. Okay? So when you have that case now, a ladder is hinged on a horizontal surface here. And this upper end rests on and then it's over a bar. So see where there is contact. This is now the contact here is being made. Let me use this. Now it's resting here, but the contact is being made. Look at this contact here. That's where the contact is. Now, the contact is going to be perpendicular to that point. That's why here, the contact is like that, as you can see. That's why the contact is like, because the point of contact is here, so this one should be always perpendicular to it. That's why you see that this point of contact, we have that being perpendicular. Then the surface resolve this vertically and also horizontally there. Okay, then when we come to case 5, ladder resting on a rough horizontal surface while upper end rests against and over a vertical wall. Now, here we have a vertical wall. Now, the case we are having, sorry, but I'm going to use this. This is the case we are having. So, okay, let me use this as the wall. When this is my wall, you see it's resting over, the ladder is resting over horizontal surface. Okay, it's resting on a rough horizontal surface. There is contact on this surface, reaction. Rough, we expect friction to be in this side. But now, this ladder is passing over while the upper end rests against and over a rough vertical wall. So this is the wall. Now, you see where this contact is going to be here, around there. That's why our contact now is not, there is a difference between having a contact there and having a contact there. When we have a contact here, it's going to be like this now. But now the contact is here. This reaction is always perpendicular to this point of contact. That's the difference. This one is passing over the wall. So the point, if it's just resting on the wall, the reaction is perpendicular to the wall. But now it's resting at this point. So this reaction is going to be perpendicular to that point, as simple as that. Now, we expect to slide going, of course, that you can see this ladder can't slide coming this side. No, slide when this lower end of it is going the other side. So when it's sliding, remember when you look at this case, when sliding, this is going to be the case. It's sliding like this. You see, the motion is this direction. So we expect friction to be the other side. This is a rare case of a uniform rod resting partly inside and partly outside the surface of a sphere. So you see the contact here is going to be perpendicular to that point. Then the contact here is the case there. Okay, because we said over hemisphere, so we consider this hemisphere to be very, very smooth. Now, there's a point note. Okay, this is the angle that this is going to make with our horizontal inside there, theta. So that's going to be the same as that. In climbing ladders, problem is to find distance that can be climbed before the limiting equilibrium is reached. One, we shall always consider the conditions of limiting equilibrium. Now, this is the case we are talking about. If you are serious, you ever try to climb a ladder and you're resting it somewhere, there is a way you rest when this ladder is not moving. But there is that point when that ladder is about to slide. So at that point when it's about, we shall consider that as the limiting equilibrium. Why? Because when you climb, this is okay. Before you reach that point, before it slides. Now, the distance we have covered from this side up to here, before or when it's about to slide, we say that there, we shall always consider conditions of limiting equilibrium. What are they about? We say, for limiting equilibrium, always the frictional force is at its maximum. It means that there we shall say that our frictional force is equal to the coefficient of friction, then times the reaction. So that's it. Whenever they want the distance someone reaches before that ladder slides, we shall consider those conditions. So that's it, members. I wish you well. Now in this lesson we are going to see examples. See you there. And don't forget to subscribe to the channel.